Hello and welcome again to the lecture on mathematical modeling of dynamic systems from the first principles. Today we will have a few more examples, and the first example today is that of stirred tank, which is shown here, a continuous stirred tank. So far what we did in the 2-3 examples that we considered, they were single input, single output systems. Some of them were linear, some of them were non-linear. We linearized the non-linear ones to obtain the linear in standard state space model of the given system. This example differs from those because it has two inputs as well as two outputs. So it is the case of a multiple input, multiple output or a MIMO system. Schematically it is shown here. There are two feeds Q1 and Q2. So Q1 is shown here, Q2 is shown here, Q1 and Q2 containing some liquid of concentration C1 and another liquid of concentration C2. They are entering the tank. These feeds are entering the tank. We have a stirrer which is continuously stirring the fluid in the tank, and thereby it is assumed that everywhere in the tank the concentration of the fluid is same, and it is Ct. And at the outflow going at the rate of QO will contain the same concentration C, which is low. The cross-section area of the tank is uniform, which is a capital A, and the liquid level in the stirrer tank, instantaneous liquid level is H. So now we have to develop the mathematical model of this system. These I have already defined. In addition to what I said, we make two assumptions more. One is that the flow is assumed to be incompressible. The fluid is essentially incompressible. And the second thing to tell is that there is no reaction taking place. Means what is that the two feeds which are coming, they may be of the same substance, or the two substances don't react with each other. No chemical reaction is going on in the system. So first we do is we consider the continuity of flow, and also we consider the mass balance of the substance which is coming in the two liquids. So first of all we see that the rate of change of liquid volume V will be, if we go back to the diagram, the liquid volume which is accumulated here in the tank, this is due to any imbalance between the incoming fields Q1, Q2 and the outgoing flow Q0. So dV by dt, the rate of change of liquid volume in the tank, will be equal to that imbalance, or mathematically it will be Q1 plus Q2, the feed 1 and the feed 2, minus the outgoing flow Q0. Now we see the mass of substance in the solution will be C times V. That C is the concentration and V is the volume. So C into V is the mass. So we again consider the conservation of mass or the mass balance. So what we will get, the rate of change of mass, this thing, will be equal to the mass rate entering, the mass flow rate entering, or that is C1 times Q1 plus C2 times Q2. This is due to feed 1 and this is due to feed 2, minus the outgoing mass, which is C, the concentration time, the outflow rate, C to Q T. So thus we have these two differential equations. Now we also note, this we did in other lecture also, that this outflow will depend upon the geometry and cross section of this flow nozzle here, the passage through which the flow takes place, and to the liquid height h in the tank. So it will be proportional to root h if other things are constant. So we write this outflow equal to mu into root h, which is because h is volume, liquid volume divided by the area of cross section. We make that substitution. So Q naught becomes mu square root of V by A, and mu is constant of proportionality. Area A is the area of cross section of the tank. We move next. So, so what we have seen now this flow rate, let me go back. This flow rate, outflow rate, we can substitute here as well as here in these two places, and then these equations will be in terms of Q1, Q2 and the liquid volume in the tank. So we get dVT by dt equal to Q1 plus Q2, they were there, minus this is the expression for QO, which we obtained in the previous page. So we will get this, and the other one is for mass. So dCT Vt by dt, the product of C and V, the rate of change of that with time. That is, these two terms are as they were. However, we have made a substitution. In place of Q naught, we are substituting this quantity. So it will be Ct multiplied by Q naught. So it is mu by root A, root mu. So now with these substitutions, we get these two equations, which are actually the dynamical equations for the stirred tank. You can see that on the left hand side, we have the liquid volume in the tank V. Its time rate of change is given in its as a mu times root A square root of V. So in terms of the volume itself and the 2 feet weights. And the other quantity, which is C times V, time rate of change of that is, again you can see it depends upon the C into V and the 2 feet weights, Q1 and Q2, multiplied respectively by C1 and C2. So these are the two, basically the system equations, the dynamical equations. Now we can linearize it. So for that we consider steady state, and at the steady state what we will have is that the feed flows, outflow, concentration and volume of liquid in the tank all will be constant. Respectively, say at Q1 0, this is the steady value of Q1, Q2 0, the steady value of Q2, QO 0, the steady value of outflow QO, C0, the steady value of the concentration C, and VO, the steady value of volume in the tank. So then what we can do is we can equate them respectively to their time rate of change will be 0, and so what we will get is, if you go back to these equations, excuse me for a moment. Yeah, if we come back to these equations, what we see that this left hand side, this one will be 0 at steady state, this one will be also 0 at steady state. So we will have Q1 at steady state plus Q2 at steady state minus QO at steady state equal to 0. This is this equation. This is this equation. Similarly, when we have a look at the second one, we are equating this to 0 And so C1 Q1 at steady state plus C2 Q2 at steady state minus CT into Q naught at the steady state, this will also be 0. So thereby we obtain this expression. Okay. And finally, because at steady state Vt is V naught and Qo is Qo naught, so we will have Qo naught equal to mu root V naught by A, which is written here, this way. So we have these three expressions at the steady state. And now we consider incremental changes around those steady state. So we assume, for example, that Q1 at any time t is Q1 naught plus delta Q1. Similarly, the change in Q2 is delta Q2. Change in liquid volume is delta V. Change in outflow is delta QO, and change in concentration is delta C. Now what we will do is, we will substitute in these expressions, we will substitute in place of the variables their steady state values plus the respective changes. So we will substitute, for example, Q1t equal to Q10 plus delta Q1t, like this. Similarly, Q22t and similarly Vt. So Vt, for example, will V0 plus delta Vt. So we make this substitution, and we also recognize that rate of change of these steady state quantities with t will be 0. So we do that, and then I leave the derivation to the student, and we will get these expressions. The first one will give d dt of incremental change in liquid volume will be incremental change in feed flow 1 plus incremental change in feed flow 2 minus the incremental change in outflow into the incremental change in liquid volume in the tank divided by 2 V naught, the steady state liquid volume. The second equation will give this. Rate of change of incremental concentration will be C1 minus C0 divided by V0 into incremental change in Q1, the feed flow 1. Similarly, another multiplier into incremental change in feed flow 2 minus QO naught divided by V naught into delta C, incremental change in concentration. So we got the two nonlinear equations describing the system. And now rest is the routine work. What we do is we identify suitable set of states. So in this case we identify delta V, the incremental change in liquid volume in the tank, and delta C, the incremental change in concentration of the liquid. So these two as the state variables, and state vector is thus x equal to x1, x2, which is delta Vt and delta Ct. Inputs are the two feed rates. For the linear system, these are incremental changes in the feed rates around their respective steady state values. And the output y is the incremental change in outflow and the incremental change in concentration of the substance in the liquid. So with these, we can now express the equations obtained previously into the state space form. So let me show how. So we see that delta V t by dt is equal to delta Q1 plus delta Q2. These are the inputs. However, this is the state delta Vt. and the quantity which is multiplying to states is, or the coefficient is this. So this goes in the A matrix. So it is here QO0 by 2B0, and it is not multiplying to the other state, so 0. So this into x1, that is coming here, this into x1, and it is not depending on the other state, so that is why we have a coefficient 0 here. And the two feed rates, they are coming, delta Q1 and delta Q2, each multiplied with 1 time delta Q1 plus 1 time delta Q2. So we have in the input matrix a 1 here as well as a 1. U is the vector, delta Q1 plus 1 into delta Q2. The second one is rate of change of concentration. So d delta Ct, that is state x2. So we have this row corresponds to x2, and we see that this depends through this on itself. So that minus Q0 naught divided by V naught is the coefficient which is appearing here. So that is the only coefficient in this row in that matrix. And other two coefficients, they are the coefficients of the inputs, the two feed rates. So this into Q10 and this into Q20. These are the two feed rates, multipliers to the two feed rates. So these two quantities go in the input matrix here and here. So we get the state equation as x dot equal to this as the A matrix and this as the B matrix. So AX plus BU. This is A and this is B. Output is, one is the concentration and other is the outflow, these two quantities. So first one is the outflow, second one is the concentration. Now outflow, we got the expression in one of the previous slides here, still in the previous slide. Outflow is QOT equal to mu, this quantity, and this was linearized subsequently. So delta QO we got expressed. I'm sorry, I'm not getting the expression, but then delta QO is QO naught by 2VO into XO. And the concentration delta C is the other output. So delta C is the second state itself here. So we get a 1 here. So here we get both the state and the output equations. The given system was of course nonlinear. It was linearized. Before that we identified the point of equilibrium and the condition of equilibrium. We identified the suitable set of quantities which could be considered as state variables. Inputs were already known in the beginning from the discussion. And the output we identified as the outflow Q and concentration. Thereby we obtained this as the A matrix, this as the B matrix, each of 2 by 2. This system is interesting. It is 2 input, 2 output and 2. So that is why all matrices are 2 by 2. We move to now the second example, which is that of water level in a pressurized compartment, which I am calling as control compartment. So this system is idealization of zone control compartments in the liquid zone control system of large pressurized heavy water reactors. You might be aware that India has a number of pressurized heavy water reactors, and few of them are in the category of large pressurized heavy water reactors. Two are at Tarapur. They have the capacity of 500 megawatts electrical, and few are of 700 megawatt electrical capacity. They are at Kakrapar and Rajasthan. One or two are either commissioned or in the commissioning stage, and others are in the construction stage. So these reactors, 500 megawatt electrical PSWRs, pressurized heavy water reactors, and 700 megawatt electrical pressurized heavy water reactors. Similar reactors are there in Canada, etc. These reactors use a system called as liquid zone control system for regulation of power and power distribution in the reactor. And this system consists of zone control compartments. And one of the zone control compartments is shown here in this slide, here on the right. So essentially, this is the zone control compartment. It is pressurized to a pressure PZ, and it is connected between one water inlet header, which is maintained at pressure PI, and one water outlet header, which is maintained at pressure P0. So actually, PZ is maintained relative to P0 at a higher level compared to the pressure equivalent of HT. So essentially, PZ minus PO, the compartment pressure, minus the water outlet pressure, this is much larger than rho G into H. And so the level variations in the compartment, these level variations will not reflect into a significant changes in the output. So the assumption here is that PZ and PO, their difference is chosen in such a way that despite the level variations in the compartment, the outflow will remain constant. This is the assumption, and this is how the system is operated. Inflow, of course, can be varied depending upon the proper positioning of the control valve. So the positioner of the valve is impressed with a time dependent signal ET, or the input to the system is ET. And because of that coil current in the positioner, the pressure on the actuator changes, which we saw in the modeling of the control valve earlier. And this pressure changes on the diaphragm of the actuator result into changes in the force on the moving parts, and thereby the valve stem moves, either it opens more or it closes more, and when it is constant, then the valve remains at a constant position. So if the valve is at a constant position, the liquid inflow will be constant, the water inflow will be constant. If it opens more, then the water inflow will be larger than its value at the equilibrium, and if it closes relative to that more, then the water inflow will be lesser compared to the water outflow. So if QI is greater than QO, the dH by dt will be positive, and if QI will be less than QO, then dH by dt will be negative. And if these are equal, then dH by dt will be equal, dH by dt will be 0, or level will be constant. So this is the key to operation of this system. And when reactor power has to be maintained constant, this liquid level has to remain constant. And if the power around this zone control compartment is to be changed, or the zone in which this zone control compartment is situated, there the power can be changed by changing this liquid level. And once the required power has been achieved, then liquid level can be brought to the equilibrium. This is the way system operates. Of course, this knowledge of the system operation helps in developing the mathematical model which is usable, closer to the usable model. It represents the situation in the system rather more realistically. And that is what I was telling, that domain knowledge is quite useful when we develop the mathematical model of the system. Anyway, so we continue. The aim here is to be able to develop the mathematical model of this zone control compartment. These are the various quantities. At the cost of some repetition, let me introduce them to you once again. Pi is the header pressure here. Pz is the compartment pressure here. Po is the outlet pressure here. Differential pressure Pz minus Po is maintained at a constant value, as I said. And so the water outflow Qo is constant. Qi is the time varying, is the input quantity dependent on the valve position. So it is the water inflow to the compartment. Z is the inflow control valve position. E is the signal impressed to the control valve. This is the input. And H is the water level in the compartment. Now we see the mathematical model of this system. So we had considered a control valve earlier, and it was like a mass spring dashpot system. Its moving parts were like that. And the force on diaphragm was essentially resulting into the force on the stem. It was trying to position the valve. So the equation that describes the control valve is a second order equation which is given here. M d2z by dt square, this is mass into acceleration, plus beta dz by dt, this is the viscous force due to gland of the control valve. Beta is that coefficient of viscous friction, and km into z, this is due to the spring opposing the motion. So all these three forces, they balance the force which comes on the actuator through air pressure, and that air pressure itself is proportional to the applied input voltage E. So that force we assume as proportional to the applied input voltage E, or Ke times Et is the force. So this second order equation essentially describes the control. The second equation we get before that, let me tell that at the equilibrium, when this compartment height is constant at h0, the control valve position will be z0, which is this, and the water inflow to the compartment will be QIO minus QO, which is this. So at the equilibrium, this inflow and outflow, they balance each other. This I said earlier also, but no harm in repeating. Control valve position equilibrium is Z0. So what will happen, that Qi, the time dependent inflow, will be Q0 plus proportional to Zt minus Z0, the valve opening relative to its equilibrium position, valve displacement relative to its equilibrium position, multiplied by the pressure difference P1 minus Pz square root of that into a constant of proportionality. So Qi is a constant, proportionality constant, because we are assuming even Pi and Pz to be constant. So a constant into the change in valve position relative to the equilibrium valve position. That is the inflow depending upon the valve position. Ahead, we see that rate of change of liquid level in the tank will be essentially due to unbalance between the inflow and the outflow. So many liters per second or cubic meters per second entering the compartment, so many cubic meters per second going out of the compartment. Accumulation will be Qi minus Qo cubic meters per second. And that divided by area of cross section will give the rate of change of liquid level in the compartment. So dH by dt is essentially Qit minus Qo divided by A, and A is the area of cross section of the zone control compartment. Now we try to linearize the system by considering incremental changes around the equilibrium operating point. So first thing we do is we assume that the control valve moves relative to its equilibrium position Z0. So incremental change in position is delta Z, which is Zt minus Z0. And equilibrium signal, that input signal, changes from E0 to Et, and so the incremental change is delta Et. Corresponding inflow change we saw in the previous page, delta Qit will be Qit minus Qo, the equilibrium outflow, which is also equilibrium inflow, and this will be equal to constant into delta Z, the valve position. So with this knowledge, this dHt by dt, if we substitute here H naught plus delta H in place of Ht, in place of Qi, Q naught plus delta Qi, then we are going to get this expression. D delta Ht by dt equal to delta Qit by A, and this delta Qit we have expressed here by this. So this we substitute here and we get d delta Ht by dt equal to mu root Pi minus Pz divided by area of cross section into delta Z. So we got the two linear equations. One this equation, which is for the control valve, and one this equation, which is for the liquid level variation in the zone control compartment. And then rest is to identify the state variables and to express the system in the standard state space form. So what we do is we identify the change in liquid height delta H as one of the states, the first state, and change in valve position with respect to its equilibrium position delta Z as the second state, and the speed of the valve as the third state. So we have x1 equal to delta H, x2 equal to delta Z, and x3 equal to d delta Z by dt. Of course, input is the applied voltage and output is the liquid level in the tank, water level in the zone control compartment. So with these we see, as we have seen on the previous page, this rate of change of liquid level is this coefficient times the delta Z. So that means the first state changes depending upon the second state. So x1 dot is not dependent on x1, not dependent on x3, it is dependent on x2, which is the delta Z, the valve position. Here, it is depending on the valve position. So this coefficient we have put in the first row, second column because of that. The second state, which is the incremental change in valve position, and the third state is the incremental change in the valve speed. So we see that x2 dot is the speed, or x2 dot is x3. So x2 the derivative of x2 doesn't depend on x1 and x2, but it depends on x3 because x2 dot is x3. So we have a 1 here. And this also doesn't have any input term. So the corresponding input terms are 0, 0 in the B matrix. The third state, which comes from here, this m into derivative of the speed plus beta into the speed plus km into the position. So position is state x2, speed is state x3. If we change their sides, we take them on the right. So m into x3 dot equal to minus beta into x3 minus km into x2 plus ke into the applied input. So with this knowledge, we can write that x3 dot equal to minus k by m into x3 minus beta by m into minus beta by m into x3 minus k by m into x2 and plus ke by m into e, which is input identified as input. So x dot is given by this as the A matrix and this as the B matrix. So AX plus B. And the output Y is the liquid level, water level in the compartment. So which is proportional to the valve opening delta Z. So we have Y equal to 0 corresponding to first state, 0 corresponding to the third state, and 1 corresponding to the second state. So 0x1 plus 1x2 plus 0x3, that is the value of Y. So this is the C matrix. And so the system is given as x dot equal to this A into x plus this B into U, Y is this C into x. This is the dynamical equation in the standard state space form for the liquid zone control compartment, which is used in the large nuclear reactors. Now the next example we take is slightly specialized one, which is that of a nuclear reactor. This may not be found in standard textbooks, so I request special attention. So a nuclear reactor is a device in which a fission chain reaction is maintained, whereby the neutron flux is defined as the number of neutrons moving in a unit volume of the reactor is maintained constant. So in a nuclear reactor, essentially we have to do the operation so that its neutron flux level is constant, and that is done if the fission chain reaction is maintained at a constant rate. So nuclear reactor, the main components are core, the reflector and the coolant. And the core contains the fuel, moderator, and of course beyond this we have control mechanism to control the reactor, which also is written here in the example. So fuel in most of the reactors is uranium-235. In some reactors, which are called fast reactors, it is plutonium-239, and in very few reactors it is uranium-233 isotope. Moderator is generally light water or heavy water. This D is another form of hydrogen which has a proton, a neutron and an electron. H has only a proton and an electron, it doesn't have any. So D is heavy hydrogen and so D2O is heavy water. So moderator can be light water or heavy water. In some other reactors it can be beryllium, etc. Reflector is used to decrease the loss of neutrons. So there is a high concentration of neutrons in the reactor core. So they try to diffuse out of the reactor core, and the job of reflector is to send them back, to reflect them as much as possible back in the core. Coolant's job is to convey the heat produced in the fission event to the outside of the core, and thereby it either produces electricity or that heat can be used in any other meaningful manner. The absorbers are boron or cadmium. They may be in the form of control rods which manipulate the operating power of the reactor, or sometimes they are also used, of course, a different system of rods to shut down the nuclear reactor. So essentially, the key to reactor operation is to be able to operate it at a constant neutron flux or to change the neutron flux in the desired manner. And it boils down to controlling the rate of fission reaction. To introduce a little more, this diagram explains the fission event. So we have nucleus of uranium-235. On that, a neutron bombards, and there is a probability, so not all neutrons bombarded will get absorbed, but some of those who get absorbed, they will result into formation of a compound nucleus, and that compound nucleus splits almost immediately into two fission fragments or two lighter nuclei, and this is also accompanied with release of, in some events, 2 neutrons and in some other events 3 neutrons. Also, in the fission reaction, a huge amount of energy is liberated, which is of the order of 200 millions of electron volt per fission. And so many 10 to the power 10, 10 to the power 15 fission events are taking place, and so you can imagine a huge amount of fission energy is liberated in a nuclear reactor. Control is to be able to maintain the rate of fission, thereby the operating power of a nuclear reactor. Neutrons produced in the fission, they are of two types. They fall into two categories. One of them is called as prompt neutrons. These are released almost simultaneously with the formation of fission fragments, and the time taken may be as short as 10 to the power minus 14 seconds from the time of bombardment of neutron on the target nucleus of uranium-235. Remaining neutrons are delayed neutrons. They are produced due to radioactive decay of the fission fragments. In the previous diagram, these fission fragments, they are unstable radionuclides, and many of them undergo beta decay, and while they undergo beta decay, they produce neutrons, and these neutrons are called as delayed neutrons. It has been seen that such delayed neutron precursors, these fission fragments which give rise to delayed neutrons, these fission fragments, they fall into 6 groups. There are 6 different groups of delayed neutron precursors, and accordingly 6 different groups of delayed neutrons. Their half-lives varying from fraction of a second to up to a minute, about a minute. However, one assumption is usually made that all these 6 groups of delayed neutrons, they can be combined, they can be considered as coming from only one effective delayed neutron precursor, with the effective parameters being lambda and beta. Lambda being the effective decay constant and beta being the fraction. So what we say that fission neutrons in a nuclear reactor, many of them will be prompt neutrons and some of them will be delayed neutrons. Sorry. So if nu is the total number of neutrons liberated in fission, I said that in some fission events 2 neutrons are liberated, in some other 3 are liberated, and nu is the average number of fission neutrons being liberated. Average in the average sense, not in the individual fission events. So I was telling that neutrons produced fall into 2 categories. One is called as the prompt neutrons. They are liberated almost instantaneously with the fission, and other called as delayed neutrons, which are assumed in this our case. To simplify, we are assuming that all delayed neutron precursors can be clubbed into one effective delayed neutron precursor group having the decay constant of lambda and beta is the fraction. So out of the total neutrons produced in the fission, which is nu on an average, nu times 1 minus beta will be the prompt neutrons and nu times beta will be the fraction of delayed neutrons. However, they will come through the decay of delayed neutron precursors. So nu times beta is the rate of formation of delayed neutron precursors. Rate of formation of delayed neutron precursor fission fragments. So rate of neutron absorption in the reactor is absorption cross section into neutron flux in the reactor. Rate of fission is fission cross section into the neutron flux in the reactor. So the rate of production of prompt neutrons, because each fission is giving these prompt neutrons, so this times the fission event, so this is the rate of production of prompt neutrons. And the rate of production of delayed neutron precursors is nu times beta into rate of fission interactions. So this is the rate of production of delayed neutron precursors. And so the rate of production of delayed neutrons is the rate of radioactive decay of delayed neutron precursors, and so it is the decay constant into the concentration of the precursors. Lambda into psi is the rate of production of delayed neutrons. So, and there is another thing, this neutron flux is expressed as product of neutron density and the velocity, Nt into V. Nt is neutrons per cubic centimeter per unit volume. V is the velocity, meter per second or centimeters per second. So phi t is neutrons per square centimeter per second, which is product of neutron density and velocity, and reactor power is proportional to neutron density. So based on those considerations, we obtain that rate of change of neutron density in the reactor will be equal to, this is the rate of production of prompt neutrons in the reactor, minus the neutrons being absorbed. This is the absorption rate, and this is the rate of production of delayed neutrons. So this is the net rate of production of neutrons per unit volume in the reactor. Of course, we do some manipulations. So we divide these two terms by sigma A, take out sigma A, also take out V, velocity, divide by V, and introduce these two notations which are popular in the nuclear reactor domain. So this equation as such it would have been good, but it has so many parameters, sigma F, mu, beta, sigma A, etc. So by introducing these two variables, of course this is again with some assumption, some terms are missing here in this. We simplify this right hand side to this. So we have divided these two terms by sigma A, and we have introduced V sigma A, that L equal to 1 by V sigma A, and K equal to mu sigma F by sigma A. So we introduce these definitions. So we simplify these things. You can check by doing the hand calculations that this, with the help of these two things, can be brought to this form, which has only, you can see, 1, 2, 3 and 4 parameters. K is called as the multiplication factor, L is called as the neutron lifetime, and lambda is the decay constant for the delayed neutron precursor. Beta is the fraction of delayed neutrons. So this is how the neutron density per unit volume in the core, reactor core, changes with time. Next slide, we do a little more simplification. We further manipulate this term. This is K minus K beta minus 1. So we write it K minus 1 divide by K, and that K we take in the denominator with L here. And this L by K is another quantity which is called as the pumped neutron generation time. And in an operating reactor at near steady state, K is almost 1. So L star and L are, for practical purposes, equal. So this dm by dt changes further to rho t minus beta by L star plus lambda psi. And this rho is called as reactivity. If reactivity is 0, the reactor is at steady state. If reactivity is greater than 0, then the reactor power is increasing, neutron density is increasing. And if the reactivity is less than 0, then the neutron density is decreasing. This, coming to delayed neutron precursors, their rate of change is their rate of formation minus their rate of decay. So formation is dependent on fission rate into their friction coming out of each fission. So sigma f into phi into nu times beta is their production rate, formation rate, and lambda psi is their decay rate. So again we do the manipulations with the help of the multiplication factor and neutron lifetime, which was introduced in the previous slide, these two relations. Again with the help of that, if we do little mathematical manipulation, we get this simplified expression for delayed neutron precursors. So with this, we have obtained the mathematical model of the reactor. One is this expression, other is this expression. And these two are the dynamical equations characterizing a nuclear reactor. However, they are non-linear. So what we do is we try to linearize them. So of course I have rewritten here these equations, and in the nuclear domain these are called as point kinetics equations of a nuclear reactor. This can be a starting point for a control engineer. In this, usually for uranium-235 fueled reactor with cooling by water, the values of parameters are something like this. So we consider the steady state, and at steady state the neutron density is n0, the delayed neutron precursor concentration is psi 0, then those two equations can be written like this. And because n0 is not 0, neutron density is larger than 0, then only the reactor is operating meaningfully. So at that time rho 0 is 0. This is the condition for steady state operation. And the delayed neutron precursor concentration is proportional to the operating neutron density, and the constant of proportionality is beta by lambda L. So around this steady state, we consider incremental changes. The steady state of reactivity is 0, incremental change is delta rho. Steady state of neutron density is n0 and incremental change is delta n. Steady state of delayed neutron precursors concentration is psi 0, incremental change is delta psi. These we substitute and we manipulate the equations. We make one assumption that the product of delta rho times delta n is approximately 0. These derivatives, these incremental changes are so small that their product can be ignored. So then this can be simplified as this, and the other equation, that delayed neutron precursors concentration equation, which was here, that can be simplified as this. So these two are the respective linearized equations for the nuclear reactor, and we can identify the states as delta n, the neutron density, and delta psi, the incremental change is delayed neutron precursors concentration. The input we identify as the change in reactivity and the output as neutron density. Then with the help of these equations, we can easily write the matrices A, B, C and D. D delta n is beta by L into delta n. So that beta by L with minus sign comes here. So d delta n by dt, other term is lambda times delta psi. So that lambda comes here, and plus n0 by L into delta rho. So that comes here, n0 by L into delta rho, which is U. And the second equation is for delayed neutron precursor. D delta psi by dt is minus beta by L into delta n. So beta by L comes here, and lambda times delta psi. So lambda comes here with the minus sign. And it doesn't contain the input term, so that input term matrix, that term is 0. Output is neutron density, which is the first state. So I'm sorry, this is to be written as rho vector 1 0 x. So output is neutron density 1 into x1, 0 into x2. So this is the output matrix. So we get for the nuclear reactor these A, B and C matrices. So this is the A matrix, this is the B matrix, and this one, as I told, it is 1 0, it is a row vector. So C matrix. We get this model of the nuclear reactor. That completes our chapter, and as a summary, you may please recall that we have learnt how to write the governing equations of different types of systems, how to express these equations into the standard state space form of x dot equal to ax plus bu and y equal to cx plus du. And in some cases, we have seen when we encounter nonlinear equations, we have seen how to get their equilibrium and how to convert them into linear models. Thank you. With that, we come to the end of chapter 2.